I still have my numbers typed in my calculator from yesterday. Hopefully you do too. Will be useful for like one problem. If you don't, it's not a big deal. You can just watch what I do. So we were starting this new chapter, and we talked about how there are two potential formulas from our formula sheet that can help us so far. They are, I do think arrows are in there now. The expected value and the variance. The rest of the formulas on this page are actually also going to come into play this chapter. Just not yet, not today. Soon, but not yet. Okay, so yesterday we were talking about this example with babies and their APGAR scale and their score. Yes. And it said to calculate by hand, so we did, and it was a giant pain in the rear. And then the last thing it said was, could you use the one variable stats button on your calculator and compare to what you found? And when we did that, we epically failed, and it didn't compare. And it's really, as always in life, our own fault, because we just didn't put the right buttons. Darn you, calculator. I mean, I swear it has all the knowledge if we just ask it nicely. So again, still in my, if I go to my list, I still have those values of 0 through 10, the options on the APGAR scale in my outline. I still have the probabilities of those scores, so like the probability of scoring one is really low. I still have that typed in as well. We assumed you were supposed to press stats, calculate one variable stats, and that is completely correct. However, what we didn't think to do is that we're wanting to use both our lists at once. So list needs to say L1, frequency list, put L2. I mean, that kind of makes sense. The probabilities were in L2. It would make sense for frequency list to be L2. Why did that not dawn on us yesterday? I don't know. It's okay. I went home, read my textbook, got my life together on how to put things in my calculator. I knew my calculator could do all the things. If you press calculate, seriously now all of a sudden we have the same stuff we had yesterday. Yesterday we got the expected value was 8.128. Now notice their X bar is also 8.128. We calculated the variation and therefore got the standard deviation of, let's see, we did it somewhere. 1.44, yep. I wrote 1.44 and we got 1.437, which rounds to 1.44 as well. So you and I worked really hard to do all this stuff by hand, and it turned out if we had just typed them in the list, trusted our known the correct buttons, and trusted our calculator could have done all that. It took like 20 minutes yesterday for us. Now, would I probably still do that by hand if this was a free response? Knowing me, I would. But that's just me, and I like to show too much work, which is probably a problem in life. Okay, are there any questions about yesterday's math? What kind of random variables were we talking about yesterday? They had a name. Yeah, I teach
discrete and variance and stuff.
Mm-hmm. So we were talking about discrete random variables. And I'll give Quinn, 2, and Jackson a point. We were talking about discrete random variables. So like on that score, back to the APGAR thing, if we were ranking a baby could get a score of a 2 or a 3. There was no option for a baby to get a 2.5 or a 2.2. So that was a discrete variable. We could actually count the number of outcomes, discrete variables. A continuous variable, it's not going to work as nicely. We're not going to have these same formulas. Life's not going to be as beautiful. But kind of think of how many numbers you can think of between 1 and 2. 1.234, 1.567. There's an infinite amount of numbers between 1 and 2. So if we're talking about continuous numbers, like with temperature or even with weight, because that varies all the time, it's kind of hard to do this math. So we have to have a different strategy for if we're dealing with a continuous variable. So that's what we're talking about today. It's at the bottom of page 2. A continuous random variable. Where are you? There you are. A continuous random variable is a variable that takes all values in an interval of numbers. So basically, we're not going to say like the probability of scoring exactly a 2 on the APGAR is this. We don't have that same confidence. The probability distribution of continuous random variable is described by no surprise density curve. The probability of any event, we can find that by calculating the area under the curve, which we've done. It's what we spent lots of time on in chapter 2.
Wait, so if it's normal distribution,
We're going to do z-scores exactly. That's what we're going to do in the next example. And do everything that we did just in chapter 2.
so that's why we're in chapter 2.
Yeah, that's what we already did in chapter 2. Suddenly chapter 2 is useful.
If they remember all of it.
Yeah, exactly. I need to remember all the things. All the calculator commands, all the things all at once.
Sure.
Let's see. What's it saying? Okay. And just like you would have expected, and I think you already knew, the area under the curve, under a density curve is exactly 1. And of course that corresponds to the fact that probability always adds up to 1 or 100%. Okay, so you and I are excited. We're hoping everything looks like our normal bell curve. And then we just calculate, maybe using z-scores, normal CDF, whatever method. Maybe use the empirical rule, whatever it was you used in chapter 2 and loved is about to come back into play. But if the density curve is not a normal distribution, we can't suddenly apply this curve to stuff. We can't make it happen if it's skewed a specific way. So we can use geometry. I'm going to do, there on the next page, there's one that's a normal, one that's a non-normal. I'm going to do the non-normal as quickly as I can, but a better example is actually some of the problems in your textbook that are assigned. If it has a uniform distribution, so it doesn't end up looking like a curve, it ends up looking like a box, that's going to be a better example of a non-normal density curve. And we can find the area under that. It is easy peasy because it is, we're just going to be finding the area of smaller size rectangles. So maybe we're wanting to know from here to here, so we literally are just going to do base times height to figure that out. It's not going to be that deep. And that's the ones in your textbook, and when I Googled the mess out of it, most of the non-normal ones that come up in stats class, we try to normalize everything. So most of them are going to be normal. But the few non-normal examples tend to be this uniform distribution. So where on earth my notes came up with this triangle one we're about to get to is beyond me. Because I tried Googling it, and the Google answer I found said the easiest thing to do would be to integrate. No, to integrate, and they try to make it really calculus-y. Because you get, like, if you had a calculus background, we could do a lot more with stats than we're currently able to do. Okay.
For chapter 6, you have a little bit of chapter 2, a little bit of chapter 5, and now it's got some geometry too.
Yep. So chapter 6 got it all.
I hate chapter 6, is fair to say.
Well, it's actually not one. I mean, so far it kind of makes normal sense. Natural sense. Okay, so our example with a normal distribution says the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. Now choose one young woman at random, calculate her height, find the probability that the chosen woman is between 68 and 70 inches tall, make sure to draw a diagram, and answer the question in context. So all calculations if you choose to use these scores. And you're like, oh my god, I don't remember how to do this. It's fine. It's fine.
We have a question.
Yes. Okay.
Champion.
It's fine.
The Greek god of calculus.
Call her height. Why? Yeah, I meant to say call her height. Thank you. Okay, so we're praying it looks something like this. We know that the middle is going to be that mean of 64. They tell us the standard deviation is 2.7. So 64 plus 2.7. We know that 66.7. One standard deviation away from the mean. 2 would be 69.4. 3 would be 72.1. And if you wanted to list it out like this, you could, and I could go the other way as well. I could subtract 2.7 from our mean of 64, so 61.3, and I could keep going. And since I'm a creature of habit and I did 3 to the right, I have to do 3 to the left. It's just in me, so. Now, did you have to go this deep? No. Could you have equally as done just a quick sketch? The means at 64, and you understand that you're wanting 68 to 70, which is above that. Like, you could have done the lazy man's way. Yeah. Good for you. I mean, it's faster.
Yeah.
So much faster.
Let's say the efficient way.
Oh, agreed that it's efficient. But, you know, I'm trying to, like, show that I understand how to apply the standard deviation to the normal curve. So, whatever. Regardless, we're both trying to find that this little region under the curve, this area under the curve. Now, we've got some options. Now, if they had asked specifically about if they had said height between 66.7 and 69.4, well, since that's within 1 and 2 standard deviations of the mean, we could have implied that empirical rule. Remember the 68, what were the other two percentages?
95.
And?
And 99.
Yeah, so you get on a point. So if they had fallen within those standard deviations, we could have done it. But 68 is not exactly 66.7, and 70 is not exactly 69.4. So we can wish it to happen, but sadly enough, that empirical rule is not going to work. So we're going to have to go to z-scores. Unless we cheat, so we're going to do z-scores, so I'm an old school person, and I'm going to do z-scores. But Hunter always did it a different way. Maybe he'll come up with it by the time I work this one out. Okay. Yes, dear. Yes, dear. Okay, so to find the z-score, if you recall, and again, I always have my handy-dandy formula sheet. Well, I do normally. Where'd you go, handy-dandy formula sheet? I can use my handy-dandy formula sheet.
What a joke.
I don't remember if that's in there or not, or if I was just supposed to know that. Good, I'm just supposed to know that. Good, I did know that. I'm going to take my number, so 68, minus the average, which was 64, and divide by that standard deviation of 2.7. I really think you would have remembered that. So that's one of the two z-scores. You type that in your calculator and you get 1.48. And so again, z-scores is when we're still using this normal curve, but now we're setting the mean at 0, and we're saying our first z-score value is 1.48 above that mean of 0. Our second z-score, so we were doing between 68 and 70, so we're going to do 70 minus that average of 64, divided by that standard deviation of 2.7, and we will get 2.22. So we're seriously wanting to know, like if we drew a third curve, like if this is 0, 1.48, 2.22, we're wanting to know the area between 1.48 and 2.22. Now we turn it into a z-score. And there are two ways we can do this. There is the calculator way, which I'm going to show you last, because I thought by now you'd come up with it. And there, of course, always is my table way. We can go to a z-table. What stinks about a z-table, if you recall, is that they tell you the probability on under the curve to one side. So we can find, let's say if this is 1.48, we can find the probability of it being less than 1.48. Or we can do 1 minus that to find the probability of it being more than 1.48, but it's hard to do the two regions at once, so we're going to have to use a little math. Okay, so I'm going to use my z-scores. I'm wanting to know, I'm asking myself the probability that's between 1.48, the probability that's between 1.48 and 2.22. That is ugly. Bless you. But again, if I'm using my handy dandy table, I'm going to need to break this down a little further. Yeah, I can actually calculate the probability that it's less than 2.22. But it'd probably be easier to then, so if we're thinking this through color-wise, if I find the probability of less than 2.22, so I find that giant, so if I find this region to the left, and I'm wanting to know it between this and 1.48, at the moment I'm double counting. There's this region that I color blue and pink, so I'm needing to discount that double colored region. So I'm going to actually subtract by the probability of 1.48. Again, this is requiring you to go way back. And yeah, I'm going to show you the way to do it in the calculator as well. But you're going to have to remember one of them. So either I know how to use a z-table, or I know how to use normal distribution in my calculator. Okay, so if I go to my table, 2.22 less than that. So let's see, where are you, 2.22? Where'd you go? There you are. 2.22 is 0.9.
It wouldn't be Z greater than equal to 1.48.
Yes. No. I'm discounting the double. I understand what you're saying, but roll with me. Okay. So I got 0.9868 and a 0.9868. And if I looked at 1.48, where are you, 1.48 on my Z table? 1.48. I know I forgot yesterday, Kenzie, don't let me forget today. And it's 0.9306. So I'm going to do 0.9868 minus 0.9306. Again, I got both those numbers from that Z table. And if I type that in my calculator, I get 0. I don't know.
0.562.
Bless you. So one 0 point being helpful. Which kind of makes sense. So it's a really small thing. So there's about a 5.6. Let's say there's about a 5.6% chance that a woman chosen is between 68 and 70 inches tall. Which makes sense because 68 and 70 are both extremely above that mean of 64. 68 inches is how many feet?
More than
5'8". It's 5'8".
Yeah, so are there that many 5'8" to 6 foot women that we know? No, there's not as many. So no wonder it's a small percentage of 5.6. Like, naturally, this makes sense. Do I actually think you probably remembered how to do all that with the z-table, especially considering we were wanting to do, like, a region. Us wanting to know, like, if we had just wanted to know below 68 or just above 70, sure. But the fact that we wanted to know between 68 and 70, do I actually think you would have used your z-table? Probably not. You probably would have found the area under the normal curve using your calculator. How to do this using our calculator. Do you remember what button we're supposed to press?
second parts.
Normal CDF.
Yeah, so we're doing second bars and the normal CDF, and they can get them another point for that. And literally, so what took me 5 steps and 5 minutes to explain, Hunter can do in 2 seconds. So I'm going to do the normal CDF, which we got to by pressing second bars, which is true.
He always knows the buttons.
He does. And so the lower height was 68, the upper height was 70, the mean was 64, and the standard deviation was 2.7. Now, you and I had already turned this into z-score, so could we have done our 1.48, 2.2, mu of 0, and standard deviation of 1? Absolutely. but his way is so much easier. There's no way we could make a typo with this. If you're going to do this and put it on your paper, it's good to have, you need to explain 68, 70, 64, 2.7, and furthermore, in order to make sure you're getting the entire E, you better put like lower, upper, and literally everything you typed in on your screen. This was my mu, or my mean. This was my standard deviation. That way they don't just see the words normal CDF and think you're crazy. Chapter 2.
There's some in the AP packet.
Yeah,
There's some practice in there.
there are. She hadn't done that in a while. I need to give her back to her.
Well, there's two, right?
Right. She already did the first one.
Oh,
Okay, so again we get 5.6%. So either way, Hunter and I both get 5.6%. He has to remember less. He just needs to remember a calculator button. I actually have to turn it into Z-scores. Then use my Z table. It takes a little longer. I agree. So definitely lazy man's way and pink is the way to go.
efficient and flat.
Yeah.
I mean, there is a rounding error. 0.0561 instead of 0.562.
Well, one assumes that his is more perfect than mine. Because mine is a table that's set in stone where it says it's calculating things. So if we're going to trust anything, we're going to go with the calculator. No offense to my handy dandy table, which I love so dearly.
There's like some strange.
Exactly. Okay, so did we even answer the question? It said we chose a woman at random. We called her hot. Why? We found the probability that the woman is queen. Yes, we found it was 5.6%. Answer the question in context. That's the only thing we haven't done. So we got to relate that 5.6% to context.
If you just summarize stats in the one sentence, it'd probably be
Press the
how we can
button.
answer the question.
The probability that a young woman chosen at random is between 68 and 70 inches is 5.6%.
And we're going to give her a point for that. Young woman chosen at random is between 68 and 70 inches tall.
I love
Yes.
putting context around.
5.6%.
You can actually like understand it a little
But literally, Mackenzie's it's not like she's made up rocket science. She took the exact stem of 68 to 70 inches tall and wrote that in her words. They like it when you use their stem back at them.
We've been making kids do that a lot earlier. I was helping my brother with his math homework, and they had like the last 5 problems weren't even solving the problem, like making a question for the answers.
Oh, I like that.
That's strange.
Okay, so let's be honest.
It's gay, dude.
Almost everything in stats is about turning things into normal stuff. If it's normally distributed, I mean, like we try to make everything normalized. I highly doubt there's a free response question that's not a normal distribution. Highly doubt it. But still good to discuss things. So we do have an example with a non-normal distribution. And again, if they were to do a non-normal distribution, I assume it would be a multiple choice question. And I still think it's going to be a uniform distribution, meaning it's going to be a rectangle, not a triangle. But you know, I taught geometry for years. We can do geometry for a few minutes. Can't spend all day on it, but we can do it for a few minutes. So, we want to know, we're given this non-normal distribution, we're going to call it a curve, but clearly it's a triangle. We need to find the following probabilities. The probability that x equals 1. So that's going to be right here. Try to draw it in the middle. What's the probability of that?
But the one is at the top of
Because the area under the curve is 1. Or the area under the triangle is 1. We're going to read it on the bottom. The way we're reading the others on the bottom. Don't try to make it too deep. We've always been reading on the bottom. Don't read it on the bottom still.
I have a question.
Yes.
So when it's the bell curve, that's a normal distribution.
Yes.
And when it's a rectangle, it's
Uniform, because they're all the same height.
So
Yes.
this doesn't qualify as uniform.
No, because they're not all the same height.
So this is just known as a
Non-normal. It's just not normal.
So, if you're looking for the probability of being 1, how would you do that if it's just like 1 point on the graph?
You can't. What's the answer?
0?
The answer is 0.
Okay, cool.
Okay, so the probability of it being just exactly that one discrete point of 1 do we actually have a colored triangle in right now? Can we find the area of that? No. So it's 0. But now it says greater than 1, so they're asking like from the pink line on. And can we find the probability of that? Yeah, we can find that area. There is a set area now. We can calculate this. The formula for the area of a triangle is 1/2 base times height. So we're going to have to do 1/2. We need a number for the base. We need a number for the height. The number for the base is, of course, 1. Because from 1 to 2, we call 1. Does that make sense?
The height is 0.5.
Time
Yeah.
is
You can just assume it's 0.5.
you could use
Yeah, I assumed it was 1/2 because I was like, well, we're about halfway up.
you
sounds
could use
good.
some, trickiness.
I tried to use trickiness to the fact that it was a right triangle.
Yeah.
And
Ever say
I was
that word
thinking about
unless
it.
you have to.
so, but I'm still pretty good with it being 1/2.
But my-
So it ends up being 1/4, which is 0.25. So about 25. Yeah, I'm good with that.
Will
Good with that.
eight people be good with that?
Okay, and then the probability of less than 1.5. Well, I've already colored all over my original triangle, so I'm going to have to draw me a new one. It used to go from 0. Absolutely.
That's a trapezoid.
Leave my triangle.
Yeah.
So less than 1.5.
I'll let you do that.
So they're wanting to know this, which is a trapezoid. Agreed. Wouldn't it just be easier to find the tiny triangle and do 1 minus to find it? So let's find instead this tiny, Lord Jesus, this tiny blue triangle. And if we do 1 minus that, we'll figure out that pink trapezoid. So if I'm trying to figure out the area of this triangle, so I know again it's 1/2 base times height. I just need to know a number for the base and a number for the height.
0.5 or
I know the base is 0.5,
0.25 for the
and I
height.
assumed the height was 0.25.
So is it -16? What's that there? What's that?
I'm going to turn it all into fractions. 1/2, 1/2, 1/4.
That must be different.
So that's 1/16. I don't know what decimal that is. Should. 0.1375?
Well, no, that 0.0625. I think it's too fast.
Okay. But we're getting the drift of how we would do this. But again, that's not the answer.
Yeah, we didn't subtract.
We have to do 1 minus. So really the answer was 15/16 or
375.
0.9375 is the real answer for the pink. Again, we found the blue. We didn't want the blue, we wanted the pink. So 1 minus the blue gave us the pink. Okay, we're going to say life's good after that, because we could do D and E, but again, I spent like 20 minutes on my planning period Googling the bejesus out of the triangle ones. It's not a common thing that comes up a lot. Find the area under whatever the curve is. If the curve is a triangle, a trapezoid, or what area, find the area. Could you have found the area of the trapezoid would be a good question, and I bet you could. That would require us knowing the length of the other base.
I mean, if it's a proportion, you could just find the height that way.
Yeah. You could. I still think it'd be easier to do 1 minus the triangle though. Okay. But regardless, we're just finding the area and you did that in geometry. I'm confident you can handle that. Move on to the next page. Okay, so this is where sections have changed. So that was all 6-1. Discrete, where we had nice pretty formulas that thankfully are on our formula sheet. And then continuous, where we don't have formulas. Instead, we have to go old school, find the area under the curve. That's all 6-1. And now we get to 6-2, which has to do with transforming and combining random variables. You're like, why on earth did this come up? Okay, and that there was a good scenario in the textbook that I thought was humorous. And they talked about when you go to a fast food restaurant and you're trying to put your lid on your cup, and sometimes they don't go, but they're supposed to go because you got the large cup, you got the large lid, it was supposed to go, but it doesn't go. So there's something wrong with the lid, there's something wrong with the cup, what's wrong? So that's what so more than just one variable of just the lid. Now it's the
It's not exact, like the way you said it was the exact way my thought process happened while I was doing it.
so like is the issue the lid or is the issue the cup? So there are two different things that are changing over time. Is the issue the circumference of the lid or is the issue with the circumference of the cup? I don't
Humans
know.
are some of the most intelligent creatures in the world, and I still try to just keep on putting the non-working top on it over and over.
Oh yeah.
For someday, what compares to humans?
The smarter humans like Albert Einstein, they're
Oh, yeah. Oh yeah.
They're lizard people.
lizard people.
Oh.
Or Mark Zuckerberg.
So that's how we're gonna. That's like one way to introduce what we're about to do. Another thing to talk about would be like your current bank account. If you added $100, doesn't that change all your monthly expenses a little bit? So how would that change stats wise? Like if we added 100 to our whatever our pool or whatever it is we're doing, how would that change things? Or if we multiply everything by 5, how would that change things? So that's why we're dealing with transforming data. Well, who knows? You know, like if you go to the casino and they say today we're adding a $500 bonus, does that change your odds of winning a casino? So that's what we're looking into now. It might, but is that going to change the probability of you winning? No. And so that's what we're talking about now. Okay, so we've actually talked about this before, but as can be pointed out, it's been a long, long time since we've thought about these things. We had a word, so we're looking to see, like, if we multiply, divide, add, or subtract by a constant, so, like, if we go and we add $500 to the casino pool or whatever, is this going to change all the stat stuff we look into? We had an acronym for the stuff we used to look into back in chapter 1 and 2, CUS. And when we used to CUS,
It's the only thing I remember. Good old days.
when we used to CUS, we talked about some of these things were resistant to change.
Outliers.
Outliers could affect you, yes.
Median, and then what was the other one?
Standard
IQR.
deviation.
The IQR, the standard deviation, the range,
Wait, sounds right?
and the median. The median normally are resistant.
Right?
Yes.
I still think my family.
Oh my god.
Fans.
Meanwhile, you know, the mean, the quartiles, percentages, those things are not resistant. That's what we used to talk about, and that's still kind of what we're talking about today. I'm going to read this, but I swear we're about to work an example that kind of helps. So if you're like, that's too many overwhelming things, it's okay. If we multiply or divide by a constant, that does multiply or divide our measure of center of location. So like if we added $1,000 to the pool, obviously that changes what the mean would be that day. Or it would also change the spread. It changes how low we could go or how high we could win because we've added more money. The only thing I would add is that the spread is absolute value B, not just B. So the second dot, if you want to change it, you can. Don't know how meaningful that is to you. It does not change the shape of the distribution. So if we have a normally distributed gambling center going on today, like the odds of you winning and you losing are normally distributed, then just because we've increased the pot doesn't necessarily mean it's not still normally distributed of you winning and losing. And the only interesting thing that I would probably put a star by that you probably do want to remember is the last bullet under that says, if you're asked for a new variance, you got to find the standard deviation first, and then square the standard deviation to find the new variance. So I know it's been a while, but as we were talking about yesterday, variance, if you take the square root of the variance, you get the standard deviation. And when you and I have been dealing with standard deviation for a while, so you always want to go back to standard deviation first, and then go to variance.
What's variance again?
It's still got to deal with variability. Like yesterday we found it was 2 point whatever, and the APGAR was 8. So like so many are normally.
For the standard deviation, like, you know, the Z-score, it's how many standard deviations is away from the mean.
Yes, and I knew you asked me that yesterday, and I read it, and I was like, oh yeah, and I like almost wrote it down, saying words back to you. The definition of the variance of a random variable is similar to the definition of the variance, blah blah blah.
Sure, mood.
As would mean the average we use in a way. The definition of the variance of a random variable is similar to the definition of the variance for a set of quantity. That is, the variance is an average. It's an average of the squared deviation of the values of variables. As with mean, the average we use is a weighted average in which each outcome is weighed by its probability of taking account of outcomes that are not equally likely. To get the same deviation around the world, for the most part, you can.
I mean, mine's gonna. I think the other way is fine. You just go to the stats option and you just flip around.
Yeah, that's what I mean. Stats or second bars, and like until I see what I think I wanted.
Like just now we did the CDF thing. I know you were one. I just kind of flipped around a little.
Yeah.
I was like, oh,
Like if you're like normal curve, so it needs to start with the world normal. B or C, like.
See, that's what I'm scared about the test. Like, I'm scared of there and
No, I haven't.
I think what I'm most scared about is I'm not going to be using my calculator. Like I'll have to use the TIA form, like
No.
graph.
You don't have to.
Really? That's good.
You would use it again.
It's still just got to do variance. It's like the word implies. It's got to do with variability. So most of the scores, like with the outgar with the 2 point whatever and it was 8 point whatever, most of the scores fall between 6 and 10 because it was 2 point whatever for the variance. I mean, it's still like standard deviation. It's just not as useful as standard deviation because I mean they're related clearly. So normally we skip straight past it and go to standard deviation, except in this probability check.
Was that the N or whatever that was that we were doing with standard deviation? Or R squared or something like that?
That was the correlation coefficient with linear stuff.
So like, is the only useful thing you're looking for is just to find standard deviation?
Normally, yeah.
Okay.
I mean, we really didn't even brush over it in chapter 1 or 2 because we just went straight to standard deviation. Regardless, we're just trying to figure out how much we vary around the mean.
Sure.
Okay, I got distracted. I'm gonna focus again. And then they have these other words. So if we add or subtract by a constant, same stuff happens. It's going to add or subtract the center, so it might increase or decrease our center. It's not going to change our spread. And then if you put this information together, they have this weird formula. But y equals a plus bx, you're like, oh god. And you're like, oh no, this looks bad. So this whole section looks bad. So I'm going to stop saying words. And I'm just going to work the next example. And you'll be like, oh, okay, this is fine. Yeah, it does. It does. It's just saying that, you know, everything else is going to be affected in the same way. What's cool is that these rules, so if we add, subtract, multiply, or divide by a constant, it's going to work the same with both continuous and random variables. So our next example has to do with temperature, which you're like, oh no, that's a continuous variable. Do I need to, oh crap. But it ends up being okay. Okay, so when there's a bathtub, say what now?
Should we say O now as in continuous variable?
I mean, they're just not as easy to deal with as discrete ones. Well, was it ever? Okay, so if we go to this way, it says a brand of bathtub comes with a dial to set the water temperature. Why are we stuck on babies lately in all the examples? When the baby safe setting is selected and the tub is filled, the temperature of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. Now, if I was being terrible, yes, dear.
You select all the problems, right?
No,
Or you select the notes?
I mean,
It could be
not
you
really.
subconsciously pick one that has to do with babies.
It's PDF. I just like this same set of PDFs for this one person. I just use all their stuff, okay? They're not. I've met them a couple times. They're not.
I don't understand what.
No, she's beyond that now. She's got like grown children graduating. She's like your mom. Like she's over it. Well, no, this one's over it. Okay, so it says draw and label the standard distribution of x. So we could put the mean at 34, and we could, so the standard deviation is 2 degrees, so we could go up 36, 38, 40. You had your hand up, Jackson.
I just, it's off topic,
Okay,
like everything else in my world.
okay. Okay, so we could do that. Draw and label, blue, blue. I didn't label, but it's okay. The important part was to get to part B, because clearly you and I don't deal in the world of Celsius. You and I deal in the world of Fahrenheit. So we've got to change this to Fahrenheit. Fahrenheit. We've got to change this to Fahrenheit. Now, you and I probably already knew that Fahrenheit, the formula for that was F equals 9/5 C plus 32.
That is sure.
Yeah.
Okay, so, meaning, what was our mean when we were in Celsius?
34.
Literally, I'm going to plug in a 34 for the C. So our mean in Fahrenheit is going to be what number?
93.
Point what?
I don't know. Let's find out. Give me a second.
Is that like hot?
Yeah, 93.2. Hey,
The hot tub at the YMCA is 109.
that sounds pretty hot for a
Wait, is it 109?
Beta
Like a
baby?
little baby?
Yeah.
Yeah,
I
that's how
honestly
you
don't
get
know. I've never heard.
them.
The baby tubs that I've seen don't have a water temperature of 80, so I don't know.
I mean, 100 degrees centigrade is boiling.
The average shower is 99 degrees.
Really?
Really?
Okay.
Oh, okay.
Sure.
Well, I honestly don't know. Again,
Like,
something
it's
is math. I don't know science. I don't know.
That's good.
I don't know. Okay, so we found the new mean. Now we've got to find the new standard deviation.
Gonna fact check all that.
As for finding the new standard deviation, are we actually going to do 9/5? I know that I plug in the 2, but do I bother to add the 32?
I don't know, do you?
Yeah.
Why do I not?
That's what water meters.
Because you don't.
But why?
I'm not
Yeah,
sure.
Okay. Standard deviation was resistant. It's resistant to that 32. So, back to linear stuff. It's going to change my mean, but it's not going to change the standard deviation. Okay, so that's why it's this. So we've got our new mean, we've got our new standard deviation.
Why did you do that?
Because it said to, because here in America we use Fahrenheit, so we gotta make this in Fahrenheit. And then it says find the mean standard deviation and draw the distribution. So if we were running out of time, we would put the 93.2, we gotta go up by 3.6, 96.8, and if I kept going down this way, I get 89.6. And I think if you had done what Kenzie wanted to do, which is, intuition of I just plug in the 2 and then add 32, I think you would have realized that's way too big of a normal spread, and you would have freaked out. Like, no, my standard deviation is normally not that big. Something's gone wrong. Okay, so we'll call that on that one. Now, as for part C, it asks for, what's the probability that, I'll just use the one I've already drawn, the probability that we're between 90 and 100 degrees. Now, since this is not following exactly where my standard deviations are heading, I can't use that lovely, lovely empirical rule. God, I love it, but it won't work. So I can either do z-scores, which we know would take some time. So if you choose to do z-scores, again, I'm going to take my number, they gave me 90, minus my average, divided by my standard deviation, and I can get my 1 z-score, which is fine because it's below the mean, so that's fine. Or I could do 100 minus my average divided by my standard deviation. And so the first one you should get negative 0.89, and the second one you should get 1.89. But, and you can do that and then use the table, and I swear life works out nicely. But, of course, it would be fastest if we did normal CDF. And the lazy man's way, say 90, 100, 93.2, 3.6, and you'll end up getting
About 78%.
0.7839, which is about 78%. We're going to call it a day on that. But again, why was that useful? Because here in America, we don't do Celsius, we do Fahrenheit. So you can see if we need to do unit conversions, we kind of do need to know whether or not the standard deviation and mean are affected by the conversions themselves.